Hello, my name is Dasgupta. I'm a professor at Tata Institute of Fundamental Research in Mumbai, in India, and I work on astroparticle physics, in particular neutrinos and dark matter. It's a pleasure to participate in this very unique Cosmology from Home conference. I'll tell you a little bit about neutrinos from supernovae. And the main purpose of my talk would be to review what one can do with the neutrinos that one could observe from supernovae that explode in our galaxy mainly, but also from beyond. Okay, here's like the big picture of where these neutrinos come from. So supernovae that explode all over our past light cone, so at cosmological distances. These, of course, are very faint in neutrinos as well. And from any one of them, you can see, a fraction of a fraction of a fraction of a neutrino. So basically, per explosion, you see less than one neutrino. But on the other hand, the rate of such explosions is about a billion, just short of a billion per year. So you could detect these neutrinos, but only as some sort of a diffuse background. And this is called the diffuse supernova neutrino background. And this may soon become detectable at existing neutrino detectors such as Super Kamiokande. On the other hand, if supernova explodes in the galaxy, that's say within the 10 to 15 kiloparsec, that's the size of the visible galaxy, then you see of the order of 10,000 or even more events. This is what we would call a galactic supernova burst. Unfortunately, the rate for such events is about once per century. The rates vary. There are more optimistic rates that go all the way up to once per 30 years. But we don't really know this very precisely, but it's not very frequent. And then there's the middle ground where a supernova could explode in a nearby galaxy, let's say Andromeda or something around that. Unfortunately, that's the hardest to detect because you already lose on the flux by a 1 over r squared. And then there are not that many such nearby galaxies which are capable of hosting supernovae. The physics case of observation of neutrinos from these three classes of environments, let's say, are different. If you have a galactic supernova, you have a very high statistics observation, a very high statistics detection, and therefore you can measure all the different flavors, their energy dependencies, and so on, even the time structure of the supernova explosion. Whereas if you're looking at the diffuse supernova neutrino background, you're more sensitive to some sort of an aggregate cosmological supernova explosion rate. You're sensitive to the star formation rate, and you're sensitive at best to some sort of an average emission property of the average supernova. But that's important for a lot of things, and we will get to that later. The middle ground, as I said, is very hard. If you could detect some of these neutrinos from the neighborhood, maybe nearby galaxies, you would become sensitive to the variety of different core collapse supernova that are emitting neutrinos. So the identity of the object and the variety of the burst and so on. Now, let's focus on neutrinos from a galactic supernova for the time being. When this star explodes, neutrinos are emitted over essentially four phases. Uh, Before the star explodes, there is what is called a pre-supernova or a pre-collapse emission of neutrinos. This is because the nuclear reactions are speeding up and they emit a lot of neutrinos. These neutrinos tend to be somewhat low in flux and it's harder to detect them, though there are ideas. But then the next three phases are quite copious in neutrinos, and it should be possible to detect them if a supernova explodes in our galaxy. So the first 20 or so milliseconds of the explosion of the star is accompanied by emission largely of electron neutrinos, so the new E's, which is what is shown in the top left panel as this green curve. The other flavors are not yet being emitted at this time in the first few tens of milliseconds. And then over the first second or so is so-called accretion phase, where the emission of the other flavors picks up, but there is still a big difference between the luminosities and the average energies of the different flavors that are being emitted. And then finally, for the next 10 seconds or so, the hot protoneutron star that's at the center of the supernova cools by emitting neutrinos of all flavors. But by this time, the different flavors have acquired roughly similar luminosities and almost similar average energies. So the neutrinos are emitted from a supernova with a quasi-thermal spectrum. So you could think of a Fermi-Dirac-like spectrum, though it's a little bit more pinched or anti-pinched depending on the flavor. And uh, these neutrinos with different flavors have slightly different energies and different luminosities, both as a function of time and as a function of flavor, whether you're talking about electron neutrinos, electron antineutrinos, or the other flavors, the new mu's, the new mu bars, the new taus, the new tau bars. Now, all of this information is largely coming to us from simulations, supernova simulations. These are complex hydrodynamic simulations. The only data that we have is from the one supernova that exploded in our neighborhood in the Large Magellanic Cloud. This is supernova 1987A. And we observed about 20 odd neutrinos from that supernova. This is partly because the detectors that we had in 1987, they were much smaller than what we have now. Nevertheless, these 24 or so neutrinos that were detected, and an original handwritten slide by Suzuki is shown here on the bottom right. What you see are 4 panels. Each of them is a detector, CAM2 on the top, Baksan, then IMB, and then LSD. And the red scratches, the vertical scratches, each of them is a neutrino, an observed neutrino, with the height of the scratch representing the energy, the measured energy of the neutrino. And on the x-axis, on the horizontal, is the time at which this was detected. So you can basically see that there are about 24 or so events with roughly tens of MeV energy each and spread over about 10 seconds or so. So that roughly ties in with what the simulations tell us. And hopefully, the next supernova that we observe in our galaxy with our much larger and much more capable detectors will tell us many more details, and that's the whole point. Okay, to come back to this idea that there are effectively 3 kinds of neutrinos in the supernova context. But these 3 neutrinos and the 3 flavors, as I will tell you, are not the usual 3 flavors, the new E, the new mu, the new tau, but rather the new E, the new E bar, and the rest. The reason for this classification is that the rough temperature inside a supernova is of the order of tens of MeVs, which means that you do not produce muons or taus on shell. So there are only electrons and positrons, but no mu's or taus. As a result, you cannot have charged current interactions of the new mu's, the new mu bars, the new taus, and the new tau bars inside the supernova. Whereas the electron neutrinos and the electron antineutrinos can experience charged current scattering and annihilations. On the other hand, neutral current scatterings are there for all the flavors. In total, what this means is that the non-electron flavors, the new mu's, the new mu bars, the new taus, the new tau bars, they experience the least amount of interaction, and therefore they can escape from deeper within the star at higher densities because they don't have as many interactions. So this is shown schematically using the green line on your screen. The green line shows the non-electron flavors that decouples the earliest. And then in red are the electron antineutrinos, which decouple afterwards further out from the center of the star. And the blue shows the electron neutrinos, which decouple the last. And they have therefore the lowest, the smallest average energies. The nu mu's and the nu mu bars and so on, they have the highest average energies. And the electron antineutrinos, shown in red here, has average energies which is somewhere in the middle. Now, these neutrinos, as they escape from the star, basically from a surface which we could think of as the neutrino sphere. So they're trapped within a radius of about 10 kilometers or 20 kilometers or so, depending on the energy and the flavor. And then there's diffuse from this surface. And because this surface is, few tens of kilometers in size, neutrinos don't just escape radially, but these neutrino trajectories, they can intersect, and at any given point outside the neutrino sphere, there are therefore neutrinos going every which way. They're intersecting each other and so on. So this will become important later. Now, you might notice that I'm talking about neutrinos as if they are classical particles that with trajectories and so on. This is a reasonably good approximation because from a kinematic standpoint, neutrino trajectories are very, very classical. What is quantum mechanical about them are their internal dynamics, the way they change their flavor. And so this is a picture that we will follow, that neutrinos are essentially classical particles as far as their movement, that as their motion is concerned. So they have trajectories just like electrons do at high energy. And we are concerned about the internal dynamics, the quantum mechanical evolution of the flavor content of any one of these neutrinos, which will be an important topic of discussion later in this talk. Okay, so these neutrinos are escaping the star, and as they escape, they experience a wide range of densities, temperatures, and they participate in a number of different um, physical processes. Most important of them are the fact that they are responsible for creation of certain nuclear elements. So in our process, nucleosynthesis in particular, and they also dump a little bit of their energy back into the star, which is actually responsible for reviving the shock wave that leads to the explosion of the star. Most of you will be familiar that when a supernova explodes, 99% of its gravitational binding energy is actually being emitted into the neutrinos. And therefore, neutrinos are actually the driving mechanism of how a star explodes. These neutrinos, once they escape the star, they can go through interstellar space and eventually they get detected at Earth. And this entire journey from the center of the star all the way to the detector, neutrinos oscillate. And this oscillation can happen in many different ways. Very close to the center of the star, inside essentially the core, neutrinos are expected to not oscillate. This is mainly because the density is very high and the mixing angles are suppressed. Though there can be interesting twists to this story, we'll come to that later. At distances of about 10 to 100 kilometers, there is a very intricate kind of neutron oscillation that's called collective oscillation. I'll tell you a little bit more about that later. After, after that, inside the star, neutrinos undergo the usual MSW oscillations. These are matter enhanced or matter affected neutron oscillations. And then there can be other effects that happen in the interstellar space or inside the Earth as well. So because the neutrinos are going through such a wide variety of environments and over very long distances, the fact that these are essentially quantum mechanical particles with interesting quantum mechanical internal dynamics, there are a lot of interesting things that one can do with these neutrinos. What one can do depends on what kind of detector one is using. And here's a list of some neutrino detectors. Some of them are running, some of them are in the future. And then depending on which phase of the supernova explosion one is looking at, one is sensitive to a different set of physical effects. So for example, in the first 20 or so milliseconds in the burst phase, the energy output of the star, basically from releasing the binding energy of the 1.4 solar mass iron core, is associated with the luminosity of the electron neutrinos. And so therefore, this phase serves essentially as a supernova standard candle. And if you can measure the luminosity in the electron neutrino burst, you are sensitive to the 1.4 solar mass iron core inside the supernova. You're also sensitive to the neutrino mass ordering, which is to say whether the neutrinos have a normal mass ordering or an inverted mass ordering. This has to do with whether M1, M2, and M3 are arranged as so, or M3 is actually lighter than M1 and M2. You could be sensitive to the timing of the burst, and this could then serve as an early warning trigger to optical telescopes, which will see the optical display once the supernova explodes, maybe six to 24 hours later. Then in the later phase, in the accretion phase, you become sensitive to these collective effects, various aspects of supernova explosion dynamics. For example, there are these things called standing accretion shock instabilities. These are, wobbling of the supernova shock wave under action of neutrino heating and convective dynamics. Then you are still sensitive to neutrino mass ordering in some other ways. You could start pointing to the source because by now you've detected sufficient number of neutrinos and you have angular resolution. And then again, this is useful for alerting optical telescopes. And then later in the 10-second or so, you become more sensitive to the nuclear physics of the stellar material, many kinds of exotic physics, for example, axions, which, if they exist, would cool down the star and shorten the time over which this neutrino signal is seen. You're sensitive to nucleosynthesis, perhaps by looking at X-ray lines. And through neutrinos, you could be sensitive to how the shock moves through the star. So there are many things that one can do, and I'll walk you through some of them. So first, let me tell you about this very intriguing kind of neutrino oscillations called collective effects. So I assume that you're familiar with the standard kind of neutron oscillations, which are just two-level systems. So imagine that there are two neutrino flavors, but these flavors are not the energy eigenstates. So a neutrino that's produced in one of these flavor eigenstates, over time, will have a probability to be detected as a different flavor eigenstate because what propagates are not the flavor eigenstates, but some linear combination, a linear superposition of the two. And as a result, the probability for finding a neutrino in a given flavor that oscillates sinusoidally with time or space. Now, this is a simple one-particle quantum mechanical problem. What happens inside supernovae is quite a bit more complicated. So what happens is that one of these neutrinos, as it's going its merry way, could interact with another neutrino along its trajectory. This interaction is not a true collision in the sense that momentum is exchanged, but simply that they can exchange phase, evolution phase with each other. And this happens because of a forward scattering, a zero momentum exchange scattering. And what you see is a four Fermi diagram on your screen. So what you have in the first picture is that an electron neutrino and a muon neutrino with momentum k and q, they interact and preserve their momentum and their flavor. So that's the case that nothing has happened. But the second picture, the second Feynman diagram, shows you the interesting case where the nu e and the nu mu exchange their momenta. And as a result, the nu e becomes a nu mu, and the nu mu becomes a nu e. And this constitutes flavor transformation. And written quantum mechanically in terms of the amplitudes of seeing each of these two-particle states, what finds is that in your evolution Hamiltonian, there will be this potential, this V2, which has this off-diagonal term, the 1 in the 2, 3, and the 3, 2 entries, as you see. So this effect, which is called collective effect, because it's happening due to the collective dynamics of neutrinos acting on each other in a certain volume, can lead to interesting kinds of flavor change. And the fact that it leads to flavor change is apparent from the fact that this Hamiltonian, this potential, has an off-diagonal term in the flavor basis. Okay, so let's go into this a little bit more. Imagine that I'm trying to write down a Schrodinger-like equation for the two-level system that describes this two-flavor neutrino. So each of these neutrinos is labeled by this index I, and I'm looking at its equation. And this stuff in the brackets is the Hamiltonian. Now, whatever is in the ellipses, the usual terms, these are the standard terms which would appear because of the neutrino mass square differences and the background electrons, which also lead to this phase change on the neutrino through what is called the MSW effect. But let's set that aside for a second and focus on this first term that I've written down. You can see that it's a sum over J goes from 1 to n. So it's a sum over all the neutrinos at that location. And therefore, J actually refers to the different momenta. And this term, the ket nu J bra nu J, basically looks like the density matrix of the jth neutrino. And the coupling factor, the factor that couples the ith and the jth neutrino, is proportional to 1 minus the cosine of the angle between their momenta. So this is 1 minus pj cap dot pi cap. So this is 1 minus cosine theta, where theta is the angle between the two trajectories. There are other factors, the Fermi constant and so on, which have been suppressed here. But this gives you the basic picture of what's the operative term that leads to collective effects. It's the refractive effect of other neutrinos along the trajectory of any given neutrino. So each neutrino, you should think of that, let's say in optics analogy, as two possible polarizations. And the environment is a birefringent environment. So the linear polarization can shift to from, let's say, along the vertical to along horizontal. That's regular neutron oscillations. But now simply imagine that neutrinos exert a birefringent refractive index on other neutrinos. As a result, the rate at which this polarization shifts depends on the number and flavor content of these other neutrinos in the environment. And that's collective effects. Now, this effect, as you can imagine, and as you can immediately see, is a nonlinear effect, because if I want to know what happens to any given neutrino, I need to know what's happening to every other neutrino, because otherwise I don't know what the Hamiltonian is. So in order to solve this problem, I need to evolve, or I need to track the evolution of all neutrinos simultaneously. So this is a severely coupled nonlinear problem. Of course, one can linearize this nonlinear problem and ask, is there a tendency for the neutrinos to switch flavor, which would mean that if I start with the neutrinos being in any one of the flavor states, is there a tendency for it to start developing a small component of the other flavor state as a function of time? And if this tendency is exponentially growing, then we say that this is an instability. In fact, that's exactly what happens. So in more detail, more precisely, the equation is not a Schrodinger equation, but more like a Boltzmann equation with a Liouville derivative on the left-hand side. So what you can see is this is an I time derivative plus velocity dot gradient acting on the density matrix. There is a little typo here. This subscript on the partial derivative should be an x. So it's a derivative along space, not momentum. And then on the right-hand side, we don't have any true collision terms because we imagine that we are outside of the region where neutrinos are still scattering through momentum changing interaction, momentum changing collisions, but you still have these forward scatterings. Because of these forward scatterings, you have basically a commutator of some Hamiltonian with the density matrix. And so each of the terms on the right-hand side is of that same form, a commutator of the Hamiltonian with the density matrix. And the first two terms are the standard terms, the mass square and the MSW. And this last term is the term that I just told you about. Now you can see here that this is a really complicated problem because you have 4 derivatives and 3 integrals. And therefore, this problem has challenged our community for several decades. Now, to quickly give you a sense of what happens because of these collective effects. So if all neutrinos are in a single flavor, let's say nu E, and there are no nu mu's, and you start with all these nu E's at some high density, the mixing angle is very suppressed. And this system then acts essentially like it's pinned to that flavor, and there are what are called synchronized oscillations. These are very small amplitude and would possibly be even undetectable. However, if the system starts with a mixture of flavors, so there are both nu E's and nu mu's, let's say, as a function of energy, and then let's say there are more electron neutrinos at, let's say, low energy and more muon neutrinos at higher energy, then it turns out the system becomes unstable and neutrinos flip flavor as a function of time in an oscillatory manner, even when the mixing angles are heavily suppressed by matter. And this is because of an instability. And the rate at which this happens is actually much, much faster than delta m squared by twice e, which is the normal oscillation frequency of neutrinos in vacuum. And this is because the neutrino refractive index, this third term that I just showed you in the Hamiltonian, that provides a way for neutrinos to oscillate much faster, and even when the mixing angles are small, because it is driven by an instability. Now, this instability comes in 2 varieties, slow and fast. Even the slow is actually much faster than the regular neutrino oscillations, but we call them slow because they're slower compared to the fast variant, which is proportional to the neutrino density. So the rate of these fast oscillations are proportional to the neutrino density, whereas the rate of these slow collective oscillations are proportional to square root of the neutrino density and the delta m square, the mass square difference of the neutrinos. Okay. Now, when do these collective effects take place? This is a question that had puzzled us again for several decades, at least 2 decades. And recently, over the last 10 years, we have developed a very clear understanding of when this happens. And as I already hinted and kind of gave away the punchline, this happens when there are neutrinos of at least 2 flavors, and each of them dominates at some region of phase space. So on your left, the picture shows, this is in momentum space. You see a blue blob surrounded by a red blob. What this is showing is that for low energies, when px squared plus py squared plus pz squared is small, you have an excess of electron neutrinos. And at high energies, above, let's say, the average energy of the neutrinos, you then have an excess of the non-electron flavors, the nu mu's and the nu taus. Again, this ties in with what I just told you about why neutrinos decouple from the star in a flavor-dependent manner. We'll tell you a little bit more about that in a second. But similarly, it's not just as a function of energy, but also as a function of emission direction. You could have an excess of one flavor over another, and these excesses manifest a crossing surface. So at the border or at the interface of these regions where one of the flavor dominates and the other region where the other flavor dominates, and the interface is a surface where the number of one flavor of neutrinos and the other flavor of neutrinos are equal. And this is called a crossing of the phase-space distribution. And this crossing is necessary for having an instability. There are also sufficiency conditions for when these instabilities take place. They are a bit more involved. We won't have time to get into them. Now, why do these crossings exist? Uh, Basically, because the different flavors have different interactions. As a result, they decouple differentially. The new E's have lower energies than, let's say, the new mu's, and therefore their energy distributions intersect. Similarly, at any given point just outside the core of the star, you would find that the new E's have not yet fully decoupled, so their angular emission pattern is more isotropic, shown here on the right panel as this roughly spherical blue blob, whereas for the new mu's, which have already decoupled at a deeper zone at smaller radius, and their emission characteristic is more elliptical, forward peaked, shown in green. And then again, these two distributions would intersect at some point, and that's where the crossing comes from. The left panel shows a case where there are crossings in energy. These are what lead to the slow instabilities. And the right panel shows you crossings in angular distributions. And these are what lead to fast instabilities, the ones that are proportional to neutrino density. Now, the slow instabilities, the main thing that they do is that they exchange neutrino flavor as a function of energy over certain regions of energy. So let's say neutrinos are emitted somewhere between 0 to 50 or 60 MeV, and then there will be some portion of this energy that, the two different flavors, they just exchange their spectrum. And this can happen over multiple regions over energy, and that depends on how many energy crossings you have. And similarly, uh, for crossings in angular distributions, you can have interesting effects. These are less well understood. Let me skip this slide because it's a bit too technical and tell you. So what likely happens is that these neutrinos, which are undergoing fast collective oscillations, are oscillating over extremely tiny length scales and time scales. So this is a little numerical simulation of these fast oscillations. On the x-axis is time in picoseconds. On the y-axis, space in 0.03 centimeters, so that's less than a millimeter. And you can see that the wavelength of these oscillations and the time period of these oscillations is extremely small. So this means that this is a really, really, really microscopic phenomena. And on the coarse-grained mesoscopic picture and the mesoscopic view that we take of neutrinos in supernova, these oscillations will get averaged out. You will not be sensitive to the time-dependent or space-dependent oscillation of the flavor, but only some sort of a smeared averaged effect. And that smeared averaged effect essentially manifests as flavor equilibration. So what happens is that as a function of, let's say, momentum or energy or emission direction, the different flavors which started out with different angular distributions and energy distributions tend to take on an almost similar phase-space distribution. This is what we call flavor depolarization. This can be computed to some extent. And over the last 5 years or so, there are possibly about 100 papers which have investigated different aspects of this phenomena. And of course, only numerically, we have no observations yet, but we believe that if neutrino phase-space distributions of the different flavors, they have these angular crossings. These flavor depolarization-like effects are essentially unavoidable. The extent to which they occur and the degree to which flavor depolarization occurs is still a matter of debate, but it is believed that this is an important effect. Now, one may wonder, how can you get any kind of equilibration starting from equations that are clearly time reversible? But the answer is exactly the same as what you would have in classical mechanics. So if you ask, you have a perfectly deterministic coin which you toss, where the hell does probability of landing on a head or a tail come from? And the answer is simply that you're coarse graining in phase space. And although if you're given the initial linear upward velocity and the initial angular velocity, you will be able to predict whether the coin lands on a head or a tail precisely, because there are uncertainties associated with the initial linear velocity and the angular velocity. You lose predictivity, and you therefore describe this completely deterministic classical system in terms of probabilities. This is precisely what is happening in the context of fast flavor depolarization. The equations of motion are completely deterministic, but because this effect is happening on extremely small length and time scales, and you are smearing over those scales, what you effectively see is a kind of equilibration, which is probabilistic. Now, we have completely avoided discussing momentum changing and number changing collisions. These are very important deeper in the star, and they do also play some role in creating the conditions for these slow and fast collective instabilities. In particular, if you want flavor distributions of the different flavors to be different because they have different interactions, that naturally demands that you have these number and momentum changing scatterings. So clearly they're very important, at least for creating the conditions for slow and fast collective instabilities. But they may be more important. They may even engender some new kinds of instabilities that are driven by collisions. This is an area of intense activity, and I have given you some references here. Feel free to look at them. Now, there's a very, very exciting field with a lot of work going on, and I wouldn't have time to cover many of these theoretical developments. I give you some references, and now I will move on to applications. So the idea is that these neutrinos, which are being emitted from the supernova, they undergo collective oscillations and then the regular MSW and vacuum oscillations, and then they're detected. And these actually provide us a way of learning many different things about the star, about the universe, and about neutrinos. So the rough paradigm within which we work here is the star is actually a laboratory for fundamental physics, which was very famously advocated for in this beautiful book by Georg Raffelt. And here are two examples. The top panel shows how you can put bounds on compactification radius of extra-dimensional theories using emission of neutrinos, because basically, if there are extra dimensions, there will be Kaluza-Klein modes, and then the Kaluza-Klein modes of the neutrinos would steal energy from the star and make it cool very rapidly. The fact that this did not happen for supernova 87A, we saw basically a 10-second long burst, tells that there are constraints on extra-dimensional theories. Similarly, there are bounds on magnetic moments and neutron masses and so on. Now, let's focus on some of the new developments. So one of the new developments over the last 5-7 years is that we have started putting muons into these supernova simulations. So previously, I told you that the temperatures are of the order of tens of MeV, so they're not that many muons, but they're not exactly zero, because if you have, let's say, a temperature of 30 MeV, then the average energy is 3 times that, so that's about 90 MeV, and then your neutrino mass of 105 MeV isn't that far. So the Boltzmann suppression isn't extraordinarily strong. So there are a small number of muons present in the supernova core, and they may have interesting effects. In particular, they may allow us to put constraints on exotic theories that couple specifically to muons, let's say an Le minus L mu kind of gauge boson. And so this has been an interesting area of activity. The other interesting thing is that people have been looking at bounds on axions from supernova emission. And the idea is again very similar, that nucleon-nucleon interactions would produce axions, and these axions would steal away energy from the star, and it would make the star cool, or it would basically slow down the shock wave or one of these things. And the fact that this did or did not happen for supernova 87A, or perhaps a future observed galactic supernova, allows you to put bounds on these kind of exotic physics. Now, there are new arguments based on what happens to these neutrinos inside the stars and how they steal energies. So, for example, consider a Majoron-like particle. This is a pseudoscalar particle that couples to neutrinos, and it can steal energy from the center of the star, the way an axion would, but then it can also decay back into a high energy neutrinos. And then these high energy neutrinos would be very easily detectable at our detectors. The fact that we don't see these high energy neutrinos from supernova 87A also puts bounds on supernova. Similarly, if there's a beyond standard model particle that is produced in the supernova, if it interacts in some way with the stellar material, it can redeposit energy into the ejecta, and it can actually make the ejecta more energetic than it would have been in the standard case. The fact that this did not happen for supernova 87A again gives you interesting bounds. So by now you must be getting a sense that there is a whole industry of looking at different kinds of bounds that come from supernova explosions and observations of neutrinos from such supernova emissions. I point you to these references. Now, a very interesting puzzle that presented itself was what happens if neutrinos have significant self-interactions well beyond what is allowed in the standard model. Now, the kind of collective effects that I was telling you about, those are purely driven by the standard weak interactions that we know must exist for neutrinos if the standard model is correct. Now, of course, we've not detected neutrino-neutrino interactions through the weak interactions, and collective effects would be a way of doing that. But what's being talked about here are exotic beyond standard model interactions, much stronger than the ones that we talked about until now. What these stronger neutrino-neutrino interactions do is that they couple the neutrinos in a moment through momentum dependent scatterings, and then the neutrinos can't free stream very easily. So they form a fluid, and it's like a relativistic big blob of hot neutrinos, which tries to expand, but then undergoes lots of scatterings. For a long time, it wasn't very clear whether these kind of exotic neutrino interactions would have any effect on the supernova, and if so, in what way? Would it lengthen the burst, or would it shorten the burst? What would it do? More recently, there is some clarity on this matter. I point you to these references, and the punchline appears to be that the effect on observables like the time of the burst and the energetics of the burst is less than few tenths of percent. There are more ideas which are somewhat older. I told you about the diffuse supernova neutrino background, and we may be very close to detecting it because now Super K has been enhanced with gadolinium, and this reduces backgrounds, and hopefully within this decade or so, we could start seeing hints of this diffuse supernova background. This would be a way to learn about the star formation rate in our Hubble patch, the initial mass function of these massive stars, and so on, and possibly also some handle on certain aspects of cosmology through the distance. Yeah. Another interesting thing that one can do with supernova neutrinos is that you can use the neutrino light curve as a function of time. This is showing the neutrino light curve that would be observable at the IceCube neutrino telescope. You would have few millisecond precision on the time at which the neutrino light curve started rising, which basically points to the time at which this star bounced back. So the bounce time. And knowing this bounce time First of all, tells you when the star exploded, but more importantly, provides very interesting complementary information to gravitational wave detectors. The top panel on the right shows you what the signal would look like as a function of time and frequency if the gravitational wave observatory did not know the time at which the signal was emitted. Whereas if this extra information is fed into the analysis pipeline, the signal to noise ratio grows tremendously, and you can see that there is a very clear detection of this supernova burst using gravitational wave detectors. That's the lower panel. Okay, with that, I'll stop. I've told you a little bit about the different phases of supernova explosion, the different oscillation physics that occurs therein. There are adiabatic and non-adiabatic MSW transitions that can happen at the shocks and elsewhere in the star. But mostly I focused on a discussion of the slow and the fast collective mixing that happens due to the crossing of the phase space of neutrinos. And the detection prospects and bounds that tell us that, well, we will see neutrinos of all flavors, energies, as a function of time, as a function of direction. And being multi-messenger helps. Multi-messenger here means not just that we want detection of gravitational waves and optical light and neutrinos, but amongst the neutrinos, we would love to detect neutrinos of all flavors because they carry complementary information. And the main point is that the early explosion phase is MSW-like, that basically is like a standard candle. And then the next 1 second or so is our opportunity to detect collective oscillations and mixing all of these interesting new effects. And the late phase, the cooling phase, is when you get all emission of all the different flavors, and the spectra become very similar, but that's the phase which you can use to derive new and improved bounds on different kinds of exotic new physics. So I hope I've been able to give you a broad picture of this field of supernova neutrinos. It connects to particle physics, astrophysics, cosmology, and there is a lot of theoretical development that's still going on in this field, primarily because this is a very complicated many-body nonlinear problem. Very little exotic, assumed physics is included in here. Collective oscillations is a completely standard model kosher phenomena. It's guaranteed to exist as long as there's a crossing. Well, and certain other conditions are fulfilled by the spectra, but we certainly do not have to assume any kind of new particle or new interactions. We don't have to hypothesize anything like that. So this is very standard, but very complex. That's the reason why it has taken so long, and it is taking so long to make further progress in this field. Supernova simulations, likewise, are extraordinarily challenging simulations. They have very high dynamic range, and making progress requires not just high computational power, but severe ingenuity. Nevertheless, over the last few decades, a lot of progress has been made, and we hope that the next galactic supernova or the detection of the diffuse supernova neutrino background that will reveal many new secrets of the universe to us. So with that, I will stop. Thank you very much for listening to me, and hope to see many of you at the in-person discussion. Thanks a lot.